Hello, our participant. On behalf of PSE for Speed Company, we are delighted to be here to talk about a problem solution using ProCAFD software tool. During this session, the presentation will be divided into two parts. The heat integration through ProCAFD, which will be presented by me, Kankanok Udawong, and the process optimization and innovation part will be presented by the Chakapat Kongcharan Kipkul. From the three states in the software using the conceptual process design, the synthesis state that give the alternative flow sheet, and the design and analysis state that perform the simulation and analyze, leading to the improvement target. And the innovation state will be focused in this section. For the heat integration session, the flow of the data are listed in here. Due to the analysis step of overall summary in the earlier session, it can be obviously seen that the process heat integration is necessary for the minimum utility and environmental consumption. So in here, after the step that I have demonstrated already, step will give you the information of the stream and utility summary data. Then in this step, the data will be transferred to the process heat indication, only the stream summary of the stream that require heat and cold utility in the process. And after we got all of the stream that require heat, the stream data will be transferred to the ICAS PA toolbox that have input as a cold stream and hot stream data, and user have to define inlet and outlet stream that require utility in the process. After the specification steps are complete, the output will give the cascade diagram, the composite curve, and the GAN composite curve in here. And from step A, after we import the regular simulation result to step A, the stream summary data will be transferred to the process heat integration step. Then the data of stream that require hot and heat utility will be transferred to ICAS2. So in here, after we go to the demonstration of heat integration, I would like to give you some brief description of step 10. So step 10 is to perform the heat integration and optimization. During this demonstration, I will demonstrate you the way to do the process heat integration first. So in here, during this step, we will specify the hot and cold stream that require utility in the process and define the temperature, enthalpy, and flow rate of each stream. And then this data will be transferred to ICAS PA2. The ICAS PA2 is the heat integration toolbox that perform the energy efficiency improvement and the operational cost in the energy relating to the application reduction, including the carbon capture in power plant. And these two can be applied when performing a process optimization. And in this tool, a set of heat integration constraints that predict the minimum utility target is added in the process optimization model. And next. Now I want to demonstrate the ProCAFD software in the step of process heat integration. So first I will open the generated HDA case example that I have shown. Okay, so from the last session, I have shown the step that the problem definition that user need to insert all of the information, like defining the compound, the inlet outlet, and the reaction data in here. To step 5, that all of the feasible flow sheets are ranked in terms of the performance criteria like the energy, the carbon footprints, and product recovery. Then we consider the least carbon consumption alternative and do the simulation through both tools. And by using the simulation result, we do the economic, the sustainable, and the environmental and safety analysis. And with the result, with the overall result, we target the equipment that can be improved in the process modification. So from this step, I will first represent you the heat integration step in order to reduce the utility consumption in heat exchanger unit and get the minimum utility consumption in here. Okay, so in order to use the process heat integration step, the simulation result need to be imported in step A. So I will import the file that we have generated in the area session. And during this step, as I have demonstrated, it will read all the stream data, no matter the temperature, the pressure, and the flow rate of each stream. And then the state of stream will be defined, like how many vapor, how many liquid in each stream. Also, the equipment that necessary for process will be analyzed, like we will give you the cooling, heating, and the electricity duty that will be used in each equipment. And next, after I already import the data, the process heat indication will be ready to working on. So in here, the stream that require coal and heat utility will be analyzed and add in this data, like the coal utility of each stream pair and the hot utility of each stream pair. And then it will define that whether this is the inlet or outlet of the heat exchanger, the temperature, the enthalpy, and the flow rate will be given. In here, we also have the option that user can select or deselect in each stream, whether they would like to continue consider this stream in the process heat integration or not. So after we already have all stream, I will click Start Pinch Analysis in here. So the stream data will be transferred to iCast2, and the simple flow sheet will be written in here. Then I will click PA to transfer all the stream data to the analysis toolbox. The screen will show off the streamline that we have. And then user have to select stream either individually or click Add all inlet and outlet stream. And now it will define whether this is the feed or product stream. And then click on heat integration to enter the heat integration toolbox. And to go to the specification step, user need to click specification. And this screen will show all the stream data that we have import from ProCAFD. And now the cold stream and hot stream need to be paired. So for example, if I pair this stream like stream 1 with stream A, you can see that stream 1 will have inlets as a 300 Kelvin and outlets as a 639 Kelvin, and then click combine. So during this step, we have to do every single pair to define the pair that will be considered in the further result. So in here, since it have 14 streams, the 7 pair will be done in here. 16 and 14. So now all of the 7 pairs are added in here. Then we can press done to end the specification step. And next, I will click Add hot and cold stream. And in here, you can see that the table for hot stream and cold stream will be shown in here, same as the pair that we have defined in the specification step. And next is Cascade diagram. This will allow user to view the tubular value of each interval, like in this column. Next is a composite diagram that will allow user to view the corresponding pinch diagram and temperature driving force. The hot composite curve will be illustrated in the red color, and cold composite curve will be illustrated in the blue color. Then user can get the hot utility target and cold utility target from this curve, and the pinch analysis is located according to the temperature difference that user have defined. Next is grand composite curve. So in this curve, user can view the corresponding pinch diagram and show the target of utility load that easier to the utility placement. The figure will show the net heating or cooling requirement at each temperature interval, and heat recovery can be maximized. The pinpoint will be located in here. Next, form the composite curve and GAN composite curve that I have illustrated. The temperature in the pinch point will be illustrated in here, both high and low temperature. And next, the minimum hot utility and minimum cooling utility will be shown in this block. Also, the number of heat exchanger required. And another information that the software will give is a heat exchanger network. So despite to the process heat integration that I have demonstrated, ProCAFD can define the detailed information of the considered utility placement, and we can improve on heat exchanger unit. And now I will back to the presentation. And I will show you the upcoming feature that are under development, which is step 11, the hybrid scheme, and step 12, which is intensification scheme. And I will transfer this session to Professor Rafik so he can give you all of the detailed explanation relating to the developing feature.
Okay, thank you, Konkanok. It's just very short for me now. I will show after Jakrapath has given his presentation. I will show you how the distillation with membrane scheme that I showed you can be done. We have a prototype Excel-based tool, which we are going to convert into option in ProCAFD. So I will just show you the steps for doing this hybrid scheme. And also in a similar way, another Excel-based tool where I will show you how a process flow sheet is converted to task, to phenomena, then generate the superstructure, and then generate the alternatives. So both are Excel-based programs, very simple Excel-based programs that we are looking now how to implement them into ProCAFD. We always test first the method. After all the steps are ready, we try to program it into and put them into the software. So the actual software demonstration will be after the next presentation by Jakrapath. So Jakrapath, you can start now.
Okay, thank you to Professor Rafik. Okay, I will share the screen. Okay. Nice to meet you to all of the guests. After Konkanok have presented and show you how to perform the heat integration by using the ProCAFD software tool, in this session, I will show you some case study with heat integration and process optimization. My name is Jakrapath Kongcharan. Right now, we have already presented on the synthesis stage and design stage. So in this session, we will talk about the innovation stages, which include the simultaneous process optimization and heat integration. Once the process has been simulated on one of the commercial simulators, some of the optimization cases can be easily done in the simulator. In my session, I will show two of the case studies to perform the heat integration and process optimization. For the case study one, the HDA process, which the heat integration and process optimization will be performed sequentially in this case study. For the case studies two, the cyclohexane process, the simultaneous heat integration and process optimization can be performed with the incorporation of the PSE for speed module as an input in the Pro Tool, which I will explain later about this. So let's start with case study one. Right now, we will continue to use the HDA process like I presented before. As we have presented yesterday that in the step 5 from ProCAFD, which the program will generate the result and tell us what is need to be improved so that we can set the target for the improvement for that. In this process, we know that some of the unit can be improved in order to minimize the utility cost. So the heater and the compressor, the reboiler and the pump, which can be set as a target for improvement. So for the HDA process, we will perform the heat integration and process optimization sequentially, step by step. The first step is the simulation without heat integration. The second step is the simulation with heat integration. And the third step is the simulation with heat integration and process optimization. So this flow sheet of the HDA has been taken from the Pro2 simulation, which I will briefly tell you how the process description. The toluene and the hydrogen will be fed to the reactor section with the operating condition is shown in this box. There are one heater and one cooler in the reactor section. After the reaction has been complete, the mixture of the product will be transferred to the flush separator to separate the unreacted gas apart from the liquid mixture. The unreacted gas will then transfer back to the as a recycle stream to the feed mixture, and then the liquid mixture will then transfer to the first column, which the task of the first column is to separate the unreacted gas, the remaining gas apart from the liquid mixture. Then the liquid mixture is then transferred to the second column to separate the benzene and toluene as a top product and the biphenyl as a bottom product, which in this process, the biphenyl is the byproduct. The benzene and toluene is then transferred to the third column, which the benzene will be separated at the top product, and it is the main product in this process. And the toluene will be some of them will be purged, some of them will be recycled back to the feed mixture. So for the first step, the simulation with the heat integration, after we have evaluated all of the duty and the work, we have computed the total required energy and the total release energy in here, which the total required energy is approximately 38.2 million kilojoule per hour, and the total release energy is approximately minus 41.2 kilojoule per hour. So in the next step, we will find a way how to reduce this number, and we will see how much we can reduce it. For the step 2, the simulation with the heat integration, if we look carefully, the stream before the reactor need to be preheated from the 372 to 639 Kelvin, and the stream after the reactor need to be cooled from 639 to 300. So it's mean that these two streams can be used for the heat integration to exchange the heat for each other. Since the Pro2 have the feature that we can do the parallel simulation, we will do the heat integration separately, and after everything is all right, we incorporate the heat integration back to the actual flow sheet. So this picture here on the right shows the stream after doing the heat integration, with the stream in the green is the stream before reactor, the stream after in the red is the stream after the reactor. So we can see that because of the minimum temperature, one heater and one cooler is still required. Then after everything is all right, we can incorporate the heat integration to the actual flow sheet, which the green stream is the stream before the reactor, which is the cold stream, and the stream in red is the stream after the reactor, which is the hot stream. And we can see that in the heat exchanger unit in here, the duty can be exchanged in this unit. So now let me show you the demonstration of the simulation program in ProCAFD in heat integration. So from this flow sheet, we can see that in this part, the heat integration has already been incorporated into the flow sheet. So in this unit, we can click on this unit, and then we can set whether which outlet temperature of which side we will set. So we use the outlet of we use the tube outlet temperature as the stream before the reactor, and then we set temperature, and then we put the overall configuration. And in this case, we assume the number of the tube and shell is 1000. And since this flow sheet take a very long time to converge, so I will just reset one unit and run in order to save the times. So in this unit, we can see how much heat can be recovered by right click and view the result. So the duty of the heat recovered by doing the heat integration is approximately 20.9 million kilojoule per hour. And for the heater before the reactor, we can look at the number, how much it can reduce. So it can reduce the heat before the reactor to approximately 800,000 kilojoule per hour. And for the cooler after the reactor, then the cooler after the reactor, we can reduce the heat by to 7.5 million kilojoule per hour. So now let me go back to our presentation. Then from the incorporation of the heat integration, the total required energy in this process now is approximately 17.3 kilojoule per hour, and the total released heat energy is approximately minus 20.2 kilojoule per hour. So the number of the total energy seem to be lower than the step one after we perform the heat integration. So in this step, the simulation with the heat integration and the process optimization based on the information from the step 9 in the ProCAFD, in addition to the heat integration of the heat exchanger. In this step, we can do something about the purge. So if we consider the part of the process which involve the gas and we can see that in the recycle stream, for example, the amount of the methane, which is the impurity in this process, is very high. And moreover, based on the ProCAFD information, the unit with the highest utility cost and highest carbon footprint is the compressor. So in order to optimize the process, we need to do something about the purge unit. So we can replace the purge unit with the separation unit, which in this case we will use the membrane to separate the methane as a purge gas and the hydrogen as a recycled gas. Thus, it can reduce the flow rate and reduce the energy consumption of the compressor. So right now we have already replaced the divider with the steam calculator, which will be assumed as the membrane, and all the methane will be put as the purge, and the hydrogen of them will be recycled back to the process. By doing this, we can reduce the energy consumption of the compressor. We can reduce the duty of the heat exchanger before and after the reactor. We can reduce the reactor duty, and we can reduce the fat separator duty. Okay, this table here shows the summary of the energy consumption, which the step 1 is in this column before the heat integration. The step 2 after the heat integration is shown in purple, and the step 3 after optimization, the column will be shown in the green, which the unit, after performing the optimization that has significantly reduced the energy I have highlighted in green. So we can see that after we perform the heat integration and optimization, the total required energy and the total release energy can be saved a lot. Okay, and even though there is the operating cost and the capital cost of the membrane unit, but with the saving of the energy, we can pay for it. Even though the detailed calculation have not been made yet, but based on our previous calculation, show that this kind of saving in terms of the energy will be paid back for the membrane within 3 to 6 months. It means that after 6 months, we can get the profit. But moreover, since the hydrogen is not going out of the process, we can reduce the carbon footprint because the compressor duty will be lower, which is another big profit. The environment will be good, the economic will be good, and the global warming potential will also be good. Now we have done the heat integration and process optimization sequentially in the HDA process. Right now, we will focus on the case study to the cyclohexane process, which the heat integration and process optimization will be performed simultaneously. But in order to do the heat integration and process optimization simultaneously, we need to add the user-added model in Pro2, which is the PSE for speed model, which the algorithm is based on the reference which I shown in the bottom here. So it's meant that the simultaneous heat integration and process optimization cannot be done with the PSE for speed model. Now let's focus on the case study 2. Next, I will further explain how to simultaneously optimize and do the heat integration in the same time for this process. The task of the cyclohexane plant is to produce the cyclohexane from the benzene and the hydrogen, which the reaction is highly exothermic and occur in the Weber phase. So the steam can be generated by the jacketed reactor. 98% conversion of the benzene to cyclohexane can be obtained. The SRK thermodynamics with the API liquid density was used in this process, and the E1 unit is assumed to have the heat exchanger area of 60.4 square meter. So let's look at the process. The hydrogen and the benzene will be fed to the reactor section. There are one heater and one cooler between the reactor. After the reaction has been complete, the product will be transferred to the flat separator to separate the unreacted gas and the cyclohexane as a product. The unreacted gas, some of them will be purged out and some of them will be recycled back to the process. As I mentioned earlier, that in the same way, we can use the information from the ProCAFD in step 9 to set the target for improvement, which these two heat exchanger can be exchanged heated and the purge need to be looked at. To show the simultaneous cost optimization and heat integration, we have at least 4 steps. The step 1, the simulation without heat integration of the initial design. The step 2, the cost optimization of the plant to determine the optimal design. The step 3, the simulation of the optimum operating point with intuitive heat integration. And the step 4, the simultaneous cost optimization and heat integration, with the step 4 is the most important step that we will show today. To optimize, we need to set the objective function. In this example, for the cost estimation, we need to use the profit as the objective function, with the profit is equal to revenue minus cost. The revenue is the cyclohexane price plus the generated stream from the reactor, and the cost is the feed, the purge, the compressor work, the flash duty, and the heat exchanger utility. So the price of the chemical and cost of the utility are given below in this table on the left, and the parameter required for the objective function will be given in the table on the right, on the bottom right. Starting with the step 1, the simulation without heat integration. So in this step, we have added 2 calculators. The first calculator is we can put the formula of the profit in, and the calculator will calculate the objective function for us. And for the calculator 2, the calculator 2 is used to compute the purge gas rate in order to balance the hydrogen and prevent the buildup of the excess methane and hydrogen. And the result of this, the step 1 is that the result of the profit without the heat integration indicate that the profit is approximately $139 per hour. So for the next step, we're going to increase this number, and let's see how much we can increase this step. In the step 2, the cost optimization of the plant to determine the optimal design. The configuration of the flow sheet in this step 1 will not be changed, and a better design is investigated in order to maximize the profit by solving the following optimization problem. So let's say that a new technology has been developed which allow to obtain a better conversion with a smaller ratio between the reactant in the feed. And also we permit that the feed flow rate can be get bigger with a higher purity of the cyclohexanes. So in this step, we will maximize the profit by varying the conversion of the benzene between this range, and we will vary we will vary the flow rate of the benzene feed, which will be in this range, which the constraint in this case will be the purity of the cyclohexane must be in this range, and the ratio of the reactant must be in this range. Then we will put all the information to the optimizer, and the optimizer will maximize the profit, which I will show you the example of the simulation in the cost optimization. So here are the flow sheet of the cyclohexane. In the step 2, which we can set the objective function in the optimizer. First, we need to choose the objective function, which in this case is the profit, which I assign in the calculator 1. Then we will maximize the profit, and then we need to define the variable that the optimizer will vary, which is the conversion of the benzene to the cyclohexane and the flow rate of the feed of the benzene. And then we need to put the constraint, which the constraint is the purity of the cyclohexane in the product and the ratio of the reactant in the feed stream. Then after that, we will run. So we can see that the simulator will run, and the optimizer will trying to find the process which has the maximized profit. So it will take some time until the solution will converge. And we can look at the number of the objective function in this table, which right now the solution has already converged, and the profit is approximately 260 something. So now let's go back to our slide. So to summarize, right now, after we perform the cost optimization, we can obtain a better profit at $259 per hour. So the next step, we will perform the heat integration, which with the heat integration is one of the target improvement in the step 5 of the ProCAFD. If we consider the stream from the inlet, if we consider the stream before the reactor, which this stream need to be preheated from 45 to 149, and the stream after the reactor need to be cooled from 224 to 49. So these two streams can be used for the heat integration to exchange the heat. And then after we have incorporated the heat integration, we can see that the heat exchanger in this unit is used to exchange the heat between hot stream and the cold stream, but however, one heater and one cooler is still required. But if we look at the profit, after performing the heat integration, the profit will drastically increase to approximately $1,118 per hour, which is very good. So the next step, we will perform the simultaneous optimization and heat integration, which is very important. In this step, we need to use the PSE for speed heat integration model, which the algorithm of this model is based on the reference that I have put in the bottom by Professor Grossman. So we need to put the PSE for speed model as an input file for the simulator, which is the Pro2. And in this step, in Pro2, we need to put the information which include the integer vector elements and real vector elements. So in this step, we can see in the flow sheet that there is one user-defined unit in here, and the Pro2 will simultaneously do the optimization and heat integration in the same time if we put the PSE for speed model, which I will show in the demonstration. So let me close this one and open the step 4 simulation files. Okay. It will take some time. Okay, then we can see that for the module that we have put, it will be defined as the user added model in here, which when we run the simulation, the Pro2 will simultaneously perform the cost optimization and heat integration in the same time. So we can add the data for the heat integration in this module, and we will try to run it to see the result. So it will take some time until the solution converges, and the profit will be shown in this table. Which during this one, the Pro2 will simulate the optimization and the heat integration in the same time. So right now we can obtain the higher profit, which is approximately 1,242. And moreover, we can look at the output of the model, which we can right click on this file with the notepad, and we can see that the result of the model will be printed here. So there are many iterations that this model need to run, and I will skip to the last iteration, which is the iteration that reach the convergence. So the data of the input that we put, which consists of the hot stream and the cold stream, will be in here, and the model will evaluate the heat integration, which we shown in this result, and we will discuss in the presentation. So the result of the heat integration is shown in here on the bottom of the right hand side. So as a result, we can see that this one indicates that all of the heating utility can be provided by the process itself and not via the external utility. An important remark to give here is that because the dimension for the heat exchanger E1, which is the heat exchanger before the reactor, is fixed, so the total heat that need to bring the stream before the reactor to reach 149 Celsius could not be obtained with this heat exchanger. So an alternative has been found from this information. The flow sheet of the best alternative of the heat integration has been shown in this flow sheet. So we can see that we can see that the hot stream leaving the reactor will finish the heating with the reactor feed in our constrained heat exchanger, and then start the heating of this stream with the hot side output stream. Then all of the results are summarized in this table. As we can see that the profit has been increased from the step 1 to the step 4 with the I have list the information of the cycle 1 to cycle 4 in here. So from the cycle 1, the original simulation, the profit is just 140, but after we perform the optimization, the profit can be increased to approximately 260 something. And then after we perform the optimization and heat integration sequentially, the profit can be increased to 936 something. But however, if we use the PSE for speed heat integration model and perform the optimization and heat integration simultaneously, the profit can be increased up to $1,247 per hour, which is very good. Because of this PSE for speed model, it can help us to consider a new way and a better alternative. The objective of the sustainable process design have been achieved through the optimization and the heat integration simultaneously by using this model. Because of the PSE speed model, the design variable were also modified slightly. This new value would not have been found if the simultaneously optimization and heat integration have not been done. The further improvement is possible through the process intensification, but we have not studied it. So thank you for your listening, and I will end my presentation here.
Okay, so thank you, Jakrapath and Konkanak. I will briefly stop sharing so I can share my screen. So I will briefly show the two examples with Excel-based program before Professor Pistikopoulos will give his lecture. Okay, so the first one I want to show, both are Excel-based program. I'm not an Excel-based program expert. I hope it will work. So let's see. Without the zoom, it was much faster. I don't know why it is slower now. Okay, can you see the screen with the Excel?
Yes.
Okay. So what you see is that we transfer the Pro2 or let's say simulator file, the flow sheet that we have simulated. So once this flow sheet is there, we have a conversion of the flow sheet to S file. So we click there. The S file information is there. The reason why we have the S file is that from the S file, it is easy for us to identify the unit operations. So we click on the S file. It lists out the separations that are taking place. And then we can say, for example, we want to give it a driving force. I'm just giving any value. So for this ED, the driving force is, let's say, 0.7, and I want to run. So I click there. It draws the reboiler duty versus distillation purity curve corresponding to that distillation. I can give my product purity that I want, 0.95, for example, and my cutoff point is 0.85. So that means, and it also tells what is the maximum recommended cut. So what I want to say is that I want a product of 95% purity, and I want to switch after 85%. When the distillation product becomes 85%, I want to switch to a membrane unit. And then I return. And then it finds out that the energy saving in this case is 42%. And then I can go to the membrane calculation, and it has found a membrane in our database with the permeability and separation that needed to be done. And for that membrane, it has calculated everything. And then we have a small database of different membranes with first is the driving force. For different driving force, we already have the curve of purity versus reboiler duty. And then we have different kinds of curves for alkenes, alkanes. So always the curve is like that. Up to a certain point, distillation is very good, but the final purity, it's not very good. So that's where we want to replace. And then the membrane database. So this is now working. We have checked it for many systems. Now we are going to implement it into ProCAFD as step 12. So step 10 you have seen. Step 11 is a lot of integration with the external simulator. But step 12 again will be all ProCAFD. We just have to convert this Excel program into ProCAFD. So I will close this, and then I will open the intensification example. So just like in the previous example, we we first introduce the flow sheet that we want to look at. And then we convert the flow sheet into S file. And then we analyze the S file. And it says these are there is the reactor and there is the separators with all of these. Then we say generate the PBVs. So it tells these are the phenomena building blocks. Then we say, okay, generate the SPBs. Then it generates the SPBs specifically for this, not the alternatives. And then we ask it to generate intensified solution. Now, there is a big step between these two that I'm not highlighting, but I will explain to you. So if we say generate, then it generates the top 4 alternatives. Now, how does it do all this very fast? We have this method. We have, based on the method, when it converts the flow sheet and it knows the S file, so it knows which unit operations are there. Unit operations are converted to task with a table like this. So we have unit operation, we have task, we have phenomena building blocks. So as soon as we know the unit operation, we can get the task and we can get the phenomena building block. And then we have a list of all the separation operations, the feed phase, the task, the PVBs, and the SPBs. So it just extract them from them and put them in here. And then based on those SPBs, it generates this superstructure, because it knows that there are 3 steps after the reactor for the compounds that come out of the reactor. This is the different alternatives possible. This is the different alternatives possible. This is the different alternatives possible. So in this example, we are not generating all the alternatives possible. Just to demonstrate, we use 4 alternatives. And then if you want to see the intensified solution, you click there and you go down and you see the intensified solution. Okay, so just a very simple example showing exactly what is the workflow, how it is done. Because we have put them as rules and as databases, getting to the superstructure is quite easy. And because we have in the background the models for each of those boxes in the superstructure, we can do easily the calculations. And then when we want to do the simulation, we have models for reactive distillation, divided wall column. All we have to do is say how many stages, which are the compounds, what are the specifications, which we have from here. We put that and then we do the rigorous simulations. So that very briefly is the presentation of the hybrid and the intensification schemes. And before I hand over to our very important guest speaker, I will take any questions you have, and then we will go to the invited speaker. Do you have any questions?
One question. Please share some reference for PBB and SPB structure method for further study.
Okay. Well, actually, in the list of references for my second lecture, computer-aided process intensification, I've given all the references, and the references, all of them will give you all the details you need for PBB and SPB.
Another one is the phenomena of DWC and distillation seem to be the same, or I'm seeing it wrongly?
Where did you mean? Did you mean the which presentation file did you mean?
So Fran said that in the Excel just now.
Oh, in terms of phenomena, the distillation and dividing wall column is the same. It's just the number of phenomena, what we called the SPBs. The SPBs will be different, but the PBBs will be the same. Because the PBBs are the basic phenomena, we combine them to form the SPB, and then we find out how many of the SPBs will be used in a distillation column or the dividing wall column. So those numbers will be different. I think, not going back now to the Excel file, as far as I remember, we were showing the list of PBBs, not the final SPBs. Okay, any other questions?
That's all for the question now.
Okay, so it also brings us the possibility to start on time. And Professor Stratos Pistikopoulos is already logged in. Welcome, Professor Pistikopoulos. Very briefly, I will tell a little bit about you, and you can say about yourself the remaining.